All right, hello and welcome. Today, we're going to crock into one of the most, beautiful and powerful ideas in all of mathematics. It's called the Fundamental Theorem of Algebra. Now, I know that sounds super intimidating, right? But trust me, by the end of this, you're going to see how it elegantly solves this massive problem and just creates this perfect, complete world for numbers. So, let's dive in. So, where does this all begin? Well, it starts with a puzzle that looks super simple. Check this out. X squared plus 1 equals 0. Okay, pretty basic algebra, right? We just move the 1 over and we get x squared equals -1. But now, stop and think about that for a second. Think about all the numbers you know and love. Positives, negatives, fractions, any of them. Can any of those numbers, when you multiply it by itself, ever give you a -1? And the answer is nope. No way, right? I mean, a positive times a positive is positive, and a negative times a negative is also positive. So within the entire system of what we call real numbers, basically everything you can plot on a number line, this simple little equation literally has no solution. It's just a hole, a really frustrating gap in our mathematical toolkit. And listen, this wasn't just some minor inconvenience. We're talking about a major, major roadblock. For centuries, you had mathematicians just wrestling with this fact that some of their most basic tools, polynomial equations, were just unsolvable. They couldn't do it with the numbers they had. Something had to change. They needed a fix.
So, what did they do? Well, they did something kind of incredible. They invented a solution. It was this totally bold, brilliant move. They just defined a new number. They called it I for the imaginary unit. And its entire job, its whole reason for existing, was to be the number that is the square root of -1. And just like that, with this one clever little patch, our unsolvable equation, x squared equals -1, suddenly had an answer. The answer is I.
And that one little number, it unlocked a whole new dimension. Seriously. Welcome to the world of complex numbers. Now, every number in this world looks like a plus bi. The a part, that's just a regular old real number that you're used to. And the bi part, well, that's the new imaginary bit. But here's the really cool part. This new system includes all the old real numbers. They're just complex numbers where that b part happens to be 0. So we didn't replace our number system, we just expanded it, made it bigger and better. Okay, but this raises a kind of scary question, doesn't it? We patched one hole, great, but what about all the other equations? What about some crazy polynomial like x to the 5th plus 3ix plus 7 equals 0? Are we gonna need a new number for that? Did we just open a giant can of worms? Are we gonna have to keep inventing new kinds of numbers forever? And this is where the fundamental theorem of algebra comes riding in to save the day. It slams the brakes on that whole scary thought process. It gives us this beautiful, complete, and final answer. It basically tells us, nope, you can stop inventing, you're done. Okay, so here's the formal statement. Let's translate that from math speak into plain English. Non-constant just means the equation isn't something boring like y equals 5. Single variable means it only has one letter, like x, not x and y. And complex coefficients means the numbers in the equation can be complex themselves. So what the theorem guarantees is that no matter how nuts your polynomial looks, as long as it follows those simple rules, it is guaranteed to have at least one solution, one root, in the complex number system. No exceptions. Yeah, and this amazing property has a special name. We say the complex numbers are algebraically closed. Think of it like this. All the questions and all the answers are inside the same box. You never, ever have to go outside the world of complex numbers to find a solution to a polynomial. That's the key takeaway here. That little patch we made with the number I, turns out it wasn't just a patch. It was the final missing piece of the entire puzzle. So how does this one single guarantee lead to something even bigger? I mean, the theorem only promised at least one root. Well, here's where the real magic happens. It's a chain reaction. Once you find that one root, let's just call it r, you can mathematically factor it out. You can divide your polynomial by x minus r. And what you're left with is a new, slightly simpler polynomial that's just 1 degree lower. And guess what? The theorem applies to that new polynomial too. So you just do it again, and again, and again. If you start with a polynomial of, say, degree 5, you can repeat this process exactly 5 times. And this leads to the biggest, most important takeaway of the whole thing. A polynomial of degree n has exactly n complex roots. Not more, not less. It's perfect. It's a perfect match. Okay, so this is a really beautiful piece of mathematical theory. It's elegant, but what's it actually good for? Why does any of this matter once you walk out of a math classroom? Well, it turns out this theorem isn't just theory. It's a foundational pillar for tons of other areas of science and engineering. For starters, it gives us this super useful consequence, especially for the polynomials you see most often, the ones with just regular real numbers in them. It says that if you find a complex root, something like a plus bi, then you automatically know that its conjugate pair, a minus bi, has to be a root too. They always come in pairs. It's a 2-for-1 deal, and that is incredibly helpful when you're actually solving problems.
I mean, this example here shows it perfectly. Let's take x squared plus 4. If you're only allowed to use real numbers, you're just stuck. You can't factor it. It's what mathematicians call irreducible. But if we step into the complex world, the theorem guarantees us there are 2 roots. And sure enough, we can break it down perfectly into x plus 2i times x minus 2i. And that's the bigger point. The theorem guarantees that every polynomial can be completely broken down like this.
And this power to completely factor any polynomial, well, it's absolutely essential. We're talking about fields like linear algebra, where it guarantees that matrices have something called eigenvalues. And that's critical for everything from running physics simulations to how Google ranks web pages. In calculus, it makes some really, really nasty integrals suddenly become manageable. And for a whole field like algebraic geometry, this theorem is basically the ground it's built on. But, a result this clean and this powerful didn't just appear out of thin air. It was the finish line of a huge intellectual quest, a race that literally spans centuries and involves some of the absolute greatest minds in mathematical history. You can go all the way back to 1629, when a guy named Albert Girard basically said, hey, I think this is true. Then, through the 1700s, you had giants like D'Alembert and Euler who made some serious headway, but their proofs, they had some holes in them. Then, in 1806, the first really solid, rigorous proof came from a guy who wasn't even a professional mathematician, Jean-Robert Argand. And finally, the legend himself, Carl Friedrich Gauss, the one who gave the theorem its name, he published multiple different proofs, really cementing its place as, well, fundamental. But here's a final, absolutely fascinating twist. Get this. Despite being called the Fundamental Theorem of Algebra, there is no known proof of it that only uses algebra. Not a single one. Every proof that exists, including all of Gauss's, has to borrow ideas from other parts of math, like calculus or a field called topology, which is all about shapes and continuity. So, that leaves us with a really deep thought to chew on. If a theorem that's supposed to be fundamental to algebra can't be proven by algebra alone, what does that really tell us about how we separate different fields of math? And maybe more importantly, what does fundamental even mean if the foundations of your idea actually lies somewhere else entirely? Something to think about. Thanks so much for joining me.